So that's what you're trying to do. Whether that is interpretable or not depends on not what the task actually is solved by having localized structures or not.
So, ready?
I can also just introduce myself.
Don't worry, it will be short. Okay, hello everyone. Today we're really happy to have Jesse to give us a handy series seminar. And on a completely different topic compared to what we learned yesterday from his excellent colloquium. Will talk to us about the flavor physics from quantum entanglement. I hope, as a convention of our seminars here, please ask questions. Let's interact.
Thank you. Okay, well, thank you. As Dan said, I'm talking about something completely different from machine learning. And I'm doing something that I've done very rarely in my portfolio, which is talk about flavor physics. This is a kind of a new area for me, using a technique that I'm still skeptical of, and so looking forward to your feedback and questions. So the topic of the talk is flavor physics from quantum entanglement. So the topic is going to be flavor physics, and somehow the methodology that we're going to use is studying some quantum entanglement. And there's no obvious reason that these things should be connected to each other. And indeed, I'll tell you a little bit more about the history of this, but I'm quite skeptical about whether this connection makes sense at all. But my amazing collaborator, Socrates Stefanopoulos, he's a postdoc at MIT right now, and he basically has convinced me that at least what we've done is interesting. Whether it's actually the way that the universe works or not, not so sure. And before coming to Minnesota, we actually got the paper out the door. We've been sitting on this idea for almost a year, but finally we pulled the trigger, and so that's why I'm giving you a whiteboard talk today to tell you about this topic, and again, hopefully there'll be some lively discussion. As I said, flavor physics is rare in my portfolio. Another thing that's rare in my portfolio are titles of papers and talks that have a question mark at the end. So I don't know if people know about Hinchcliffe's rule. So Hinchcliffe's rule is that if there is ever a scientific paper, for example, that hits the archive, and the title ends with a question mark, then the answer is no. So Ian Hinchcliffe, I overlapped with him when I was a postdoc at Berkeley. He's kind of a cantankerous Berkeley faculty member. It's actually only my second paper ever that has a question mark at the end. The first paper that had a question mark at the end, it wasn't actually a yes or no question, so it doesn't fall into the Hinchcliffe rule category. And in some sense, I don't know whether I want nature to work this way that I'm going to tell you or not. It's almost more perplexing if nature does work the way that I'll talk about, but you'll see this in a moment. Okay, so we're going to be talking about flavor physics, and in the case of flavor physics, of course, we have 3 generations of quarks and leptons, and the mixings of quarks and leptons are described by the CKM matrix and the PMNS matrix. And for the purposes of this talk, we're going to ignore the masses of fermions and just focus on their mixing angles. So the CKM matrix, each one of them has mixing angles theta 1, 2, theta 2, 3, theta 3, 1, as well as CP violating phase. Common to CKM and PMNS. We won't be talking about Majorana versus Dirac neutrinos. And the goal, yeah.
I'm sorry, so if you ignore the masses, what's the point of CKM matrix?
Can you just excellent question. So ignore not fermion masses. Ignore masses in the concept. Ignore predicting masses. Let's say it that way. Ignore predicting masses. So the goal is to actually just predict these angles. And indeed, one thing that you should worry about is in a limit where masses can be ignored, what does it even mean to have a mixing angle? And that's going to be part of the reason why we talk about quantum entanglement. I'll tell you what we did, but that is certainly a reason that you might want to attack this particular proposal. So we have 4 angles times 2 for the lepton sector and the quark sector. And what a grand challenge in flavor physics is to understand where do these angles come from. What we're going to do is I'm going to give you a qualitative prediction, qualitative using this principle of quantum entanglement. that actually gives you values of these angles that are at least qualitatively in agreement with what we see experimentally. The thing that makes this different than other models of flavor is that other models of flavor are trying to, for example, explain the hierarchy of these objects through some kind of higher dimensional structure. But ultimately, you have a conservation of free parameters. That is, ultimately, if you look at the Lagrangian, so this is in comparison to, or compare it to typical flavor models that have conservation of free parameters. Where, while you might be able to understand kind of the qualitative ordering of things, for every particular angle or mass that you're trying to do, you basically have one parameter in your Lagrangian somewhere. Here, even though I'm emphasizing that I'm only making a qualitative prediction, at least in principle, it could be a quantitative one. Because we're going to be using minimization of quantum entanglement. And if you have a function that you minimize, functions that you minimize can set multiple things to some value all at the same time. And so in some senses like this, as the internet would say, one weird trick in order to get predictions for the whole flavor structure.
So
yeah.
Previous attempts at this use maximizing the quantum entanglement, right? So
You could also, there have been...
So there's also been papers where people have minimized it?
Most of the papers are about minimization, actually.
I see, so not maximization.
Well, some are max and some are min.
Okay.
And you can ask what the hell's going on, right?
Yeah. Okay.
So in fact, some sense, I'm not so much advocating for a principle as more of a calculation that we did that has a result. And it happens to be that in our context, minimization of entanglement seems to be the thing that's correlated with these sorts. But you can certainly question the philosophy. So what we're going to be doing, and again, it's not conservation of free parameters, it's different than that. We're going to be able to make multiple, okay, it's not really predictions. There's one prediction, but most of them are postdictions. Of course, we've already measured these angles apart from the CP violating phase in the neutrino sector. Multiple postdictions from one, in quotes, principle. And so what we're going to do is we're going to minimize quantum entanglement, so minimize quantum entanglement in 2-to-2 electroweak scattering. So at some level, once you choose your measure of entanglement, once I tell you to do 2-to-2 scattering, you just go ahead and compute things, do the minimization, you're done, and that will pop some numbers. Now, why you should do this particular thing or not is not so obvious. I have no idea why it works. But the thing that makes this non-trivial, and the reason why I was willing to put a paper on the archive about this, is that if you're doing electroweak scattering, then of course the charges of quarks and leptons have different electroweak charges. In particular, neutrinos in the lepton sector don't carry any electric charge, therefore they don't interact with the photon. It turns out that the photon plays a big role in this story. And so because they have different electroweak charges, that's the reason why from one principle you're able to get different CKM and PMNS matrices. So that's what makes this non-trivial. If it were something where independent of the electric charges, you got some prediction, then you would have said that quarks and leptons should look the same way. But because of the different electroweak charges, that's the reason why you get something different. And again, this differs from other models of flavor, which have to somehow advocate for why quarks and leptons are different, for example, by having different flavor structures or discrete flavor symmetries. Here, it really is one principle, and it's the electroweak physics that's telling you why they're different. Now, of course, you could ask, wait a second, maybe electric physics itself is subject to some meta entanglement principle. And, of course, we're ignoring predicting masses here, so maybe something that has to do with the Higgs as well. So what I'm doing is kind of just reporting on a calculation. And the question that we really don't know is this deep or is this numerology? That is, if you do a calculation and you get a result, people have stared at the CKM and PMNS matrices for a long, long time. It could be that you just stared at it so many different ways that you just find something that accidentally works. And that could indeed be the case right now.
Jesse, just to confirm, ignoring predicting mass, you mean you work strictly in the mass basis, and so you're discussing the.
That's right. So that means I work, as you said, in the mass basis.
And study the structure of.
And you study the structure of CCAM, assuming the mass basis, and everything is going to be entanglement with respect to a preferred mass basis. And that turns out to be very important. And in particular, if you allow the basis itself to change, then if you do the same minimization of entanglement story, what you find is that things are diagonal, but things are diagonal because you just pick the directions that things are coupling in. And so it's the misalignment between the interaction basis and the mass eigenstate basis. That's what we're trying to get at. But that means I need to fix something. And in this case, we're fixing the mass basis. And that's also something that looks ad hoc. And I should say, everything that I'm saying here is outside of the context of standard quantum field theory.
And for leptons, did you assume the neutrinos are Dirac or Majorana?
It's irrelevant.
Oh,
it doesn't matter. As long
as
as
the electric interaction. That
right. Because it's interaction and the masses, we're not trying to predict the value of the masses. And in terms of the interactions, those are entirely done by PMNS independent of whether it's Majorana or Dirac.
Yeah, but there are two more independent angles, right?
The additional Majorana phases in principle, which we have no control over. They don't show up in electrically scattering. Okay. So we are not the first people to notice that there is this potential connection. So for previous work, if you go to our paper, you can find more of these sites. So let me just put initials just to save myself from writing. So Bean, Kaplan, Clico, and Savage in 2018, as well as Lowe and Meehan in 2021. What they noticed was that if you minimize entanglement, and here they were focusing on things like baryon scattering, minimizing entanglement led to enhanced symmetry. So for example, if you have two flavors of quarks, there's a flavor symmetry, kind of up-down, but also a spin symmetry, and you actually find that your scattering entanglement is minimized if you have a spin flavor symmetry SU4. And there's other things that happen when you have three flavors, an enhanced SU16 symmetry that emerges from this principle, which roughly agrees with what phenomenology is doing. So again, minimizing entanglement leads to enhanced symmetries, which, for the context of flavor physics, to my mind, imagine you did the same thing in the flavor sector. You would say you minimize entanglement here, unless you get an enhanced SU3 flavor symmetry of all the generations. For me, that would be not impressive. Okay? For flavor, this would be not impressive, in my view. So why is it not impressive, in my view? So let's say you have some function, I don't care whether it comes from quantum entanglement, whatever principle you want, some function, let's say the CKM mixing matrix, and you want to say for what value is that function minimized, and you tell me, oh, it's minimized if it's the identity matrix. But come on, like any type of any notion of enhanced symmetry, like if you have a function, if you have a matrix, function of a matrix, like, it's going to be minimized when it's either 0 or diagonal or some special features. And that's not impressive because that doesn't match what the CKM and PMNS matrices look like. And so when Socrates first said to me, oh, we want to do something with entanglement, and we want to show that you get an enhanced symmetry, enhanced flavor symmetry, I was like, I can give you an enhanced flavor symmetry just by imposing SU2 flavor symmetry. That doesn't agree with nature, which, by the way, is different than what was going on in these papers where they were trying to actually explain something that's approximately seen in nature, that among baryon scattering, this kind of spin flavor symmetry is something that we approximately see. So that's why it's maybe a good thing to see in that case, but would not be a good thing, or at least not an impressive thing to see in my case. And it doesn't matter how fancy this F is, doesn't matter what principle you use. If the answer were diagonal, I wouldn't be interested.
Are their answer diagonal or not?
Their answer, they didn't study electric scattering, but their effective answer is something, actually it's even more than diagonal. They find really, it's really kind of amazing symmetry structures that emerge from their study, in particular in the three flavor case. A bigger set, naively it would be SU6, but they find it SU16. So it's like a really, really cool structure. Okay, so what I think Tony was referring to is that other people, so this is other prior work. Other prior work by Verta, Latore, Rojo, and Portillo in 2017. What they did is they studied actually electric scattering type processes, but they were doing maximizing entanglement and maximizing entanglement in terms of helicity, maximizing helicity entanglement, plus some funny assumptions, which we could talk about if you wanted to. But this paper showed that if you do this, then you get a prediction for the Weinberg angle, which controls the ratio of the W and Z boson masses, which agrees with the experimentally measured value. So they get a quarter, and their experimentally one is like 0.22, just close to 0.25. And the way that they get this value, the reason why they get something that's not trivial, is that this comes from competition between different effects. And so that's buried in this plus dot dot dot. That it's not just maximizing helicity entanglement, but maximizing helicity entanglement subject to a particular type of constraint. That constraint induces competition. That's why you get a non-trivial mixing structure.
But sine squared theta, though, I mean, in a gut, it would be 3/8, and then it's through renormalization that you get the value today. So what does this mean?
I mean, it's equivalent to when people say that they can predict, 1/137 as being a special number for alpha EM, but that's of course the low energy value. That's not the high energy value. So what you would argue, if you really believe that there's an entanglement story, you would argue that nature sets whatever values it's going to do, but somehow there's this UVIR connection, such that the parameters that go into your Lagrangian at a high scale are such that when you do scattering at irrelevant scales, you end up getting that structure.
So you're saying that's taking into account renormalization?
But that is, these calculations are done at the electroweak scale and not at the high scale. And we're going to do the same thing here. In fact, you're going to see very explicitly. You have to decide what scale you want to evaluate this minimization at. It's going to be scale dependent. And depending on what scale you do, you're going to get different answers. And the ones that match up with nature correspond to doing the calculation at the scale of the scattering that you're studying. And again, from the UV perspective, the traditional quantum field theory perspective, we usually think of a theory being defined in the short distance, and then we have whatever manifestation in the IR. Here it's saying that somehow you already know where you're going to hit in the IR such that you minimize entanglement at that level. Which again, you can argue whether it's reasonable or not. But the important lesson is just that when you have competing effects, that can get you away from having kind of diagonal type structures or minimal type structures. And maybe that's what we're going to see in our case.
But okay, but if you were to do things at higher energy, would you see the running of sine squared?
No.
Would it go to a 3/8?
So it appears to be that the answer is no.
Well, in that case, you have to choose either guts or this.
You have to choose all sorts of things. I mean, this structure is outside of the standards of quantum field theory. You're trying to make a prediction about how nature works, and we don't know ultimately where these values come from. And I think flavor is a particularly interesting playground for this because you don't really need 3 generations to explain, for example, the fact that we exist and we have a periodic table. So you can't even appeal to anthropics for the flavor sector, so it's kind of crying out for some kind of organizing principle. Normally, we have flavor models with conservation of free parameters, where there's some free parameter for every element of the Euclid matrices. And here, we are saying that if you follow this strange procedure, which, yeah, as you say, you have to decide whether you think it's high scale, low scale, this weird UV-IR compatibility, that it will give you a prediction. And again, you are, I will assure you that I am more skeptical about this idea than all of you. This is a kind of a nuts thing. Unfortunately, as I'll explain, I was unable to kill this idea. And so let me go you through the history of this project.
So sorry,
Yeah.
just to understand, I mean, maybe you'll make this
Yeah.
clear in a second,
Yeah.
but so you're gonna show that actually a non-diagonal CKM matrix will have smaller entanglement than even a diagonal one?
Yeah.
Because I would kind of think if you
Yeah.
just have no flavor changing, that
Yeah.
would be the least.
Yeah, that's what I thought,
Okay.
and that is not true.
Like you said, it's gonna come from a competing effects?
Yeah.
Or maybe
Yeah,
you'll just
I'll say what
explain
the
it.
competing effect, but basically, it's gonna come from, competition between flavor changing and flavor preserving interactions.
Oh, okay.
And interference terms turn out to be relevant, and that's why
I
you
see.
get competition.
It's because you have multiple diagrams.
Because you have multiple diagrams, yeah, okay. So here's the history of the project, so this was with, Socrates, or as I keep calling him, Socrates. Because, but if you want to have a Socratic dialogue, so this is, you know, how this collaboration began. So you start off with Socrates, and what does he says? And he says, I want to predict CKM from something like max or minimum entropy, or entanglement, sorry, maximum entanglement. We're not doing an entropy style argument, though of course there's a connection between entanglement, entropy, those things, but it really is some measure of quantum entanglement, not just the number of states, but particularly entanglement across a bipartite separation. Okay, so that's what he says. I want to do this, and of course, me knowing the literature here, I'm like, well, you're going to get something diagonal, and so what I said is, okay, you can do this, but VCKM of order 1 is not interesting. So don't get me involved. Unless you can show me that you can get a Cabibbo angle, so Cabibbo angle, that's the mixing between the first and two generations in the quark sector. Unless you can get me a Cabibbo angle that's an order 10%, I'm not buying it. And moreover, that unless you have some type of competition, then you're always going, I mean, if you think about how physics systems work, the only time you get interesting answers is if you have two competing effects that balance against each other. And this is something that when I teach quantum mechanics to undergraduates, I emphasize that unless you have two competing effects, then your ground space structure is pretty simple. So you better show me that there's competition, and that's the only shot that you might have to get a Cabibbo angle that wasn't equal to 0 degrees. And by the way, other people have done scattering, these people did this, and they did not find competing effects. So I'm not buying. Okay, Socrates comes back to me, and he says, okay, well, let's do electroweak scattering. And with electroweak scattering, we can have up and down quarks, and up and down quarks can exchange Z's and gammas. And this is a flavor preserving process because there's no FCNCs, no flavor changing neutral currents. If you start off with one generation of uptype, you're going to end up in the same one, same thing for the down. So this doesn't want to generate entanglement. So minimizing entanglement, well, this thing already wants to minimize entanglement. It doesn't want to correlate flavors in a quantum mechanical way between the up and the down. You start off with charm strange, you're going to end up with charm strange, this process. But there is a competing diagram where you have W exchange, where you have up-down going to up-down, and of course these things know all about CKM. And actually the history of the calculation is something that's more interesting. So first, what he did was just with a Z, and Z only leads to a Cabibbo angle, which is 13 degrees, which is the standard model value. Unfortunately, once you put the gamma interference in there, then you get 6 degrees. So our dreams of getting a numerically precise prediction were dashed by that. But this is what you have: see competition between two processes. In particular, if you start off with charm strange, charm can become any number of things. It could become strange. It could become something else. Same thing the other way. And then these two diagrams interfere with each other, and so there's interesting interactions between the identity matrices here and the CKM.
Yeah, could you provide just a very simple calculation to substantiate this? I mean, I'm kind of confused about how you use the word entanglement.
Yes, well, first of all, I'm going to define entanglement for you. So part of the challenge of this project is what is the precise definition of entanglement? So I think you would agree that in this process, generically, actually, if you start off with some kind of up-down state, then generically you would get entanglement in the sense that you don't generically, so if I have ij here, you don't generically end up with KL for definite generation number. So this would be no entanglement. This is saying that I have a bipartite system, and this is perfectly correlated with that. Entanglement appears when you have a sum over different possibilities, with some weights. So say you have multiple different possibilities, and that multiple different possibilities is your measure of entanglement. So entanglement here, we're saying that you want to go away from product state-like structure into something where you have correlations in the final state. So if I have just this type of diagram, and this type of diagram itself doesn't give you a sum. You start off with definite mass eigenstate values, and you end up with definite. Entanglement is generated generically by this, and now you just have to ask, well, what is your precise meaning of that? What's your precise definition of entanglement, which we'll get to in a moment.
And is it going to be important that this is tree level and not loop level? Because at loop level now, all parameters come in the standard model.
Yeah. So, but it's worse than that. It's worse than that. So, here we're talking about bipartite entanglement. Okay, but once you consider loop level processes, then we know from the optical theorem that anytime you have a loop level process, you also need to think about just tree level processes with an additional emission. If I had an additional, for example, photon emission here, in fact, that has an infinite singularity for emitting a photon. Now, how do you define your bipartite separation? So it's even worse than just you introduce loop calculations and it changes your numbers. In fact, that's what we need. This difference here, if you actually look at what a typical one-loop calculation will do, a typical one-loop calculation can actually explain that difference. If we're just one-loop calculations, that would be totally fine. In fact, this is what we want, because we don't get the right values.
Exactly, yeah, you wouldn't.
But the problem is that then, once I do one loop, then I have to think about, well, how do I combine this stuff together? How do you think about entanglement in a quantum field theory? If this weren't quantum field theory, if you're dealing with just Hilbert spaces, if everything was regulated on a lattice and put in a box, fine. I know how to do bipartite separation. But if you're doing Fock spaces, where you have variable numbers of particles, I do not know how to define bipartite separation in a way that really satisfies me. In part because this weirdo thing that the divergences in real and virtual, they happen with different multiplicities. And so then how do I define separation of things in a way that is consistent with that? And talking to experts who think about, for example, positivity of scattering amplitudes, they also have the same problem of how do you deal with these infrared divergences. But we're not getting away from that. And the hope is that this will inspire one to first come up with better measures of entanglement, and then that work in Fock spaces, and then two, you do the one-loop calculation, and it'll of course match.
Yeah, exactly, yeah.
Or you find some reason why you can ignore IR degrees of freedom, get rid of the photon, and then we have a beautiful equation.
So maybe I'm missing something here, but if the CKM matrix were exactly diagonal, then doesn't even the second diagram also just give you exactly what you put in? Like if you start with charm strange, you always get charm strange?
So here, so you have to be careful. So so you always get the same thing. So if you put let's say top strange, top would give you bottom. So it changes. That would give you bottom, and then strange would give you down. Strange would give you charm. So it could change the flavor, but it still wouldn't have a sum. However, these diagrams would still interfere with each other, and you get something non-trivial. So actually, the CKM matrix being diagonal, that turns out to not be the solution here, because you have interference between these terms.
Okay. And
the interference between those terms ends up generating contributions in the sum. So because right, that makes sense.
Yeah, I get it.
So it doesn't preserve this changes flavor even without CKM being diagonal. This changes flavor of the whole structure. If that makes sense.
Right. Yeah.
So that's actually why you get CKM that doesn't want to be diagonal. If it were diagonal, then you would find that you have this extra entanglement structure. So to minimize that, that's why you actually want to turn on a little bit of mixing, such that you can actually have more often the time for these kind of funny intergenerational structures can actually give you something that would kind of undo the entanglement, if you like. Makes sense?
Okay.
Yeah.
So again, by this process, what is the mixing you get for third generation?
Fourth. So in terms of the prediction that we're going to get the prediction for CKM, just to tell you, I'll say this in a moment, is that 1, 2, that's 6 degrees. and then 2, 3, and 3, 1 is basically 0 degrees, though that's dependent on what scale you do it. And because you have 0 degrees, that means that the CP violating phases is undefined. So if you look at our paper about our prediction, it says you turn on CCAM and you don't turn anything else on. However, when you actually look at the details, you realize the squiggle of 0 is squiggle 0, not equal 0. Because actually it's scale dependent, and depending on exactly what scale you might want to turn on the middle of this. So we're not really making a prediction for these angles other than they're small. And then one of the corrections, if you could possibly put them in, would definitely distort them in a way that would be interesting.
How does the scale dependence come in?
So the scale dependence comes in for kind of 2 reasons. One reason that it comes in is the relative importance of Z, gamma, and W. Z and W are roughly the same strength. So it's really kind of how much the Z versus gamma matters. Gamma is something that has a forward singularity as well. So gamma really wants to say that if particles scatter and they basically just want to pass by each other, and they want to pass by each other in a way that preserves flavor. So when that dominates, you get a different prediction than if these things are kind of comparable size. So that's one way that the scale comes in. The other way that the scale comes in is from the fact that we are fixing the masses. So if you're too low of a scale, your states don't include heavy states. And so now you have to choose what scale you want to do your evaluation on. Do you want to make it possible to make top quarks or not? And
Okay, so
that
you
gives
have
you the answer.
thresholds and you have the momentum transfer.
Does it say we get?
You have thresholds and momentum transfer.
Thresholds, momentum transfer, yes. And then what we're going to do to avoid this photon singularity, so unfortunately there's a forward T-channel singularity, what we're going to do is actually we're just going to look at 90-degree scattering, where S and T, or where T and U are the same. And you can also argue about why that's the right thing to study.
And what about dimension 6 operators?
That would also change things. So
I was going to say, I mean, how big of an effect would that be?
So the actual minimum here, if you actually look at the entanglement measure, okay, it goes down, I'll put it like this. This is a function, so this is a function of theta Kadibo, some measure of entanglement. And then, you have 6 here, you have 13 here, and there's like kind of this trough here. That's pretty, so it definitely goes down here, so it doesn't want to be at 0, but it's pretty flat. And loop calculations, that would move this around, and then, yeah, you put in a dimension 6 contact term, and then you're right.
Yeah.
So Socrates, being a good model builder, says, oh, we can use this to actually predict that there should be new physics at a particular scale. Our calculation didn't work.
Exactly.
And then you actually introduce the dimension 6 operators to make it work.
Right.
So that's, of course, his way of thinking.
And does that what?
Sure. What do you mean, does it work? It's like
it's obvious because
it's like that is you have some function of a scattering amplitude that's super sensitive to perturbations. Therefore, you put in something of the right scale. So now I think the better question that you can ask is, if I put something in there, what's the scale of suppression? And can you imagine a new physics that would be compatible with what we know? And that one, we haven't done it in detail to find out whether you can kind of sneak this in without it already being seen. And my guess is that we won't be able, that it needs to be, with like the lambda scale has to be close to a TeV-ish, and TeV-ish stuff involving quarks, that's typically ruled out. But
I mean, I would be very skeptical that higher dimension operators at the level at which they're bounded would change terribly much
the entanglement structure.
the entanglement structure. If it did, I would wonder whether you're defining something that's meaningful.
Yeah, absolutely. Well, there's a couple of other things to say. So, let me not go down that road. That's not the road that I view this as a model building opportunity. I view this as an opportunity to try to understand entanglement and quantum field theories better. And again, I haven't done the numbers. I think you're right. I mean, my generic expectation is that these operators would be suppressed at the 10 TeV scale, and therefore, like experimentally at minimum, and that you would not be able to fix things. But again, it's quite delicate, and the fact that turning on and off the photon move things by an order of 1 amount, that's gives you some sense about how delicate this entanglement measure is. Okay, so Socrates did this calculation for quarks, and what did I say? My response was, okay, whatever. It's just one number. This is not impressive, just numerology. and a numerical coincidence, and I said, I bet you'll find that VCKM is going to equal VPMNS using your principle. Yeah, you found this competition, but it's going to be the same competition for neutrinos, which of course is not the way that nature works. The question?
I was gonna say, are you gonna still tell us what the entangled, so you drew this graph here.
Yeah, I'll definitely do this, yeah.
Okay, you'll tell us what that is.
I will, as much as time allows, I will tell you the whole story, as much as I can tell you. So I'll tell you what this, I had to tell you what this measure is, I tell you what the answers are, yeah.
Did you do it for the two flavor case first, just to check theta C?
That's indeed what we do in our paper.
Okay.
So our paper, the original paper was supposed to just be this done. And in the two flavor case, you can go, it's pretty easy to do the calculation. And you churn through it, you get an answer. So, I think part of the.
Yeah, two generation.
Yeah, two generation.
Not two flavor.
Two generation case, thank you,
Yes,
thank you.
of course,
Four flavors, two generation, thank you. So the two generation case, that's what we were gonna originally do. And I just said, hey, that's the thing we've been sitting on for a long time. It's like, but it's just one number. And it's sensitive to all these choices that you would make. And I bet you're gonna get the wrong prediction for neutrinos. And what Socrates found out is that, of course, quarks and leptons have different charges. And for quarks, the structure that you generically get, even if you kind of modify the particular measure of entanglement, you end up getting a hierarchical CKM matrix, whereas for the lepton sector, you end up getting an anarchic PMNS matrix. And it's hard to explain like why specifically you get those different structures. Obviously, you just do the calculation, but roughly speaking, it has to do with the fact that leptons don't appear in an equivalent diagram involving neutrinos. No, photons don't appear in the equivalent diagram involving neutrinos. And with the photon not there, photons provide this kind of big push towards making things flavor diagonal. And when you remove that, then you're only left with kind of the interference thing that we already talked about, where already even with diagonal, you would have gotten kind of entanglement being generated. And that's the thing that you're trying to suppress, and you suppress it by interference.
So what was your input here? Did you fix the mass of the W and the Z, and you fix the Weinberg angle?
Yeah, fix the Weinberg angle.
So those give you ways.
Yeah, good. So in our paper, we show you how does the Kabibel angle depend on the Weinberg operator. And there's an interesting relationship that as you change the Weinberg operator, you're basically changing the strength of these two diagrams. And as you change those strengths, you get a different prediction for the Kabibel angle. So another way of viewing our work is saying that entanglement is an interesting correlation between two phenomena that are usually think about as totally separate. You mentioned gut phenomena, which tells you about W and Z mass relations, flavor phenomena. Like typically those things are not linked together in terms of the mixing angles. And here you would say they're actually correlated if you think that entanglement minimization is a principle.
But follow up with that, for the neutrino ones, right? I don't involve photon.
Yes.
Will your prediction differ if I do an electroweak theory or just SU2 spontaneous broken SU2 theory?
You mean if I didn't have so I think what you're asking is imagine that I just had W1, W2, W3.
Yes, I do the study following your procedure. Do I predict the PMNS?
Yeah. So
yeah, does Weinberg angle matters in there? Because it's not adjusting relative strengths to a large extent.
That's an excellent question. I don't know the answer. My intuition is that, and I haven't done this calculation, if you had the pure SU2 theory, my intuition is that you want to get a diagonal PMNS. That's my intuition. And so the competition is not just the mass of the W and Z, it also has to do with the coupling of the W and Z, which is different. Also remember the neutrinos don't talk to the photon, but the leptons do, and the charged leptons do it. That actually happens.
So do you include the charged leptons in the entanglement?
Yes, yeah. So
there is a photon contribution.
No, so good. So what we do is we do exactly the same thing. So what I failed to say is that everything that we're doing is for elastic scattering, elastic in the flavor sense. So while you're correct that generically, certainly at one loop, and certainly you could have like just charged leptons scattering off each other, But here, the diagram that we're looking at would be neutrino charge lepton goes to neutrino charge lepton, and the other diagram where here, because one of the gauge bosons has to end on the neutrino line, that's why the photon doesn't appear. But you're right. Once you go to radiative corrections, who knows what happens.
And then you could also exchange a graviton, right?
Yeah.
But that one wouldn't affect it.
It's also time.
Yeah, it wouldn't affect it, right?
Wouldn't affect it at the order that we've been moving up. Okay. So after this long saga, where we get something that more or less looks like experiment, and then qualitatively the quark sector, and then qualitatively you get the leptons and quarks have different behaviors because of their different electroweak charges. I said, fine, Socrates, okay, as long as you put a question mark in the title of our paper, I will sign on. And again, echoing Hinchcliffe's rule. Okay, so let me tell you the answer, and then define the entanglement power for you. So let me just tell you how impressed or not you should be. Let me just tell you the answer that we are claiming. So I did this already. So for CKM, so we have theta 1, 2, theta 2, 3, and theta 1, 3. These two are approximately equal to each other and approximately equal to 0 degrees. And this one is 6 degrees. And then versus the experiment, 1, 2 is 13 degrees. 2, 3 is 2 degrees, and 1, 3 is 0.2 degrees. Okay, so the fact that these are close to 0 is more or less okay. And again, there is some fudging. It's not like it wants to be exactly 0. It's like, depending on exactly the scale, as you'll see in a moment, of you evaluating, you get those numbers.
Do you get a hierarchy between 2, 3 and 1, 3?
That is hard to see. So the short answer is it does not appear that way. At the order that we've done, it looks like they want to be more or less the same size. So that's maybe one thing that's not satisfying, except for, again, we already discussed, flavor physics. It says flavor physics starts at 1 loop. That's where you get flavor changing nuclear currents from, for example.
In your calculation, you had said something in the beginning about ignoring masses. Ignoring the generation of masses. So we are not floating the masses in doing this calculation. So you could ask, what would happen if you floated the masses and say, do I get a prediction for the top quark mass and the charm quark mass, things like that? So we are not doing that. Okay,
and partly why we're not doing
masses.
that is because then I start to say, oh geez, do we need to worry about Higgs exchange too? And
But you could turn these predictions around, since we know there's a mass matrix and it is diagonalized.
Yes.
Then this is a prediction of the top quark or the up quark mass relative to the down quark. Or
So
the strange
we
quark.
go the other direction. We could definitely go the other direction. We could fix these numbers and then do the calculation the other way. The
Would
thing
it look worse?
What?
Would it look bad?
Oh, so we didn't do it, and the reason why we didn't do it is because we are confused about something much more fundamental. And you'll see when I do the measure of entanglement that if it seems weird to have someone talking about a paper where I'm not vigorously defending what I've done myself, this is just weird. This is a case where I'm confused why we get results that look at all like nature at all. So, and the problem with masses is that we have this question that we'll see in a second about what is the scale at which I do my calculation. But if you're moving masses at the same time as you're moving the scale, then it's not actually clear how you should think about this minimization procedure if that really is something in nature.
But you could make them follow each other.
That's right. So you could do like as like a race, like or
You just
like,
use kinematics, so to speak.
That's right. That's right. And when you do that, what you find is that actually the entanglement is not that sensitive to the masses, because once you're above a mass threshold, the particular kinematic suppression that you get is not really that big of a deal. And then, as you'll see in a moment, we actually do helicity projections as our definition of entanglement. So even like the opposite helicity contributions aren't really don't enter our calculation. So but they could, yeah.
If you're necessarily including third generation, right?
We are or not.
No, you are.
We are, yes.
Yeah. So how do you avoid having Higgs exchange? I mean, you just mentioned it, so.
Yeah, let's see, how do we avoid doing Higgs exchange?
That,
So,
I would expect
you're
that's not
strictly, so
negligible.
you are strictly speaking, sorry, give me a second. So I need to think more carefully about the size, but we are specifically doing left-handed scattering. So we force ourselves such that if I start with a left-handed state, I stay left-handed. So I'm going to do a measurement to keep me in the left-handed sector, whereas the Higgs would do a flip. Sure. And now the question which I need to think about is whether there is a subdominant piece interfacing with the mass that we have neglected. So let me talk to my collaborator about that. We did not include the Higgs, and
Because
that would affect the third generation. For the later generations, it wouldn't matter. But because the reason why we didn't think about it is because we were always saying we're doing left-handed scattering, but of course there is a mixing between left and right.
Maybe that's what drives theta 1-3 to.
That's right. Yeah, wouldn't that be amazing? Like, what if that were true? So what if I come from Minnesota, I tell this like, oh, there's a complaint that we forgot to include the Higgs exchange, and then we put in Higgs exchange in V2 of our paper, and then we get those values. Again, I'm not sure if I want Higgs to work that way or not. Okay, so then P minus, let me just tell you what the numbers are. So theta 1, 2, theta 2, 3, and theta 1, 3. So these ones are roughly the same at 29 degrees, and this one is 16 degrees, and the experimental values are 33 degrees, 48 degrees, and 8 degrees. So basically, if you squint, two angles that are roughly the same size, one that's smaller, that's the structure that you get. And then this assumes, I should say, it matters a little bit, this assumes that the CP violating phase in the PMNS matrix is pi, that's minimal CP violation. You can ask why I'm making that assumption. If you let pi float, so this one, as I said, because this thing is 0, for theta 1, 3, the CKM CP violating phase has no prediction. But there, the theta 1, 3 has a large value, and so then you can actually minimize over this, and what you find is the answer is pi, which is consistent with normal ordering best fits, if that matters to you. Okay, so you can imagine higher order corrections, shifting things around. This minimum is kind of delicate, and I don't know if you're intrigued by this, or if you're disgusted by this whole story, or probably more likely, this is your state of mind. Okay. So, but at this point, I've told you our predictions, and now the rest of the talk is about saying what our specific measure of entangling power is. Right. So let me just pause here. If there's any questions about the claim before now we go deep into how exactly are we defining entanglement?
I have a technical question.
Yes, Maxine.
Hi. So when you interfere different contributions, you're dealing with particle thresholds, right?
Yes.
What do you take, for example, if I take I don't know, up down scatters into up strange? What do you take for the strange threshold? Because this is not a trivial question, right? It's incorporated in the QCD structure. If underneath the quark scattering you scatter mesons, then it's a kaon mass threshold that you should do. If you scatter baryons, well, it's a much lower mass threshold, right? In the hyperon sector. So effectively, so I'm just wondering what.
Yes, good. So excellent question. So at the end of the day, we're going to pick a benchmark value of the scattering energy, and that benchmark value is going to be somewhere near the top quark mass. So the particular details of like what definition of the strange quark mass you use turn out to be not relevant. So that's how we sidestep this. Basically, there's this kind of look elsewhere effect that we were looking at our calculation, asking when do you get something that looks like what you see in the standard model, and basically when the values of scattering are comparable to the states involved, like all the states. So the top quark mass or the Z boson, the W, like somewhere in that range, that is where you get the prediction. So therefore, the details of the strange quark mass definition or up and down mass definition is not relevant.
Mm-hmm.
That makes sense?
Thank you.
Yeah.
How much do your predictions depend on the energy, the scattering energy?
I'll try to draw a picture for you, but if we're doing 90-degree scattering, and like you basically get the same answer through this range, and then there's a crossover point where the photon starts to matter a lot, and then the predictions go completely haywire in terms of the scattering energy. For the scattering energy, the lepton sector, as long as you're above a few times the mass of the tau, then everything is massless, basically, and you actually get predictions. These numbers are in some sense more robust because you don't see additional thresholds showing up. For the quark sector, as you go above or below the top quark mass, because there's that threshold there, you end up getting quite different behaviors. And then the detailed meaning of the entanglement matters a lot. And so we actually show in our paper extra curves that might help you figure out a better principle potentially.
Well, yeah, so I mean, in the lepton case, if you're way above the tau mass, then I would think all three of the generations are basically the same. So shouldn't you get the same predictions for all three of the angles?
So, right. And so when you think about the precise definition of entanglement minimization, so it's 3 generations, but we're doing 2-2 scattering. And so it's almost like the same reason that you can't get the diagonal matrix, because there's competition between effects. That same reason means that you can't make all the anarchic angles exactly the same, because in some sense there's, I don't know how to say
So
it.
there's going to be like multiple minima or something.
That's right.
Spontaneous.
That's right. So in particular, so something in our paper we talk about that there actually is this freedom to redefine stuff, and so what we're calling these angles, that really matters. And so then the way we're anchoring what we mean by those angles is by going down to the low energy limit where the tau is special. So the tau neutrino ends up being special because that's the one that's connected to the tau. And then you kind of continue, and when you're looking at the curves, you kind of continue, and then the memory of the tau persists. And then as you go to higher and higher energies, you end up seeing that, yeah, you can't really tell anymore which one is which. Okay, so what's our choice of entanglement measure? Choice of entanglement measure. And this is a particularly tough one because already, if you think about like quantum entanglement in scattering processes, there's already tons of entanglement coming from the fact that there's momentum correlations. So when you have scattering generically, if you have something going one direction, it's balanced against something going the other direction. And of course, if something going this direction is correlated this way. So you actually get huge amounts of entanglement just from kinematics. Okay, and if you take that part seriously, in some sense, you completely wash away anything that has to do with flavor. So our choice of entanglement measure is going to be one where we're going to just focus on flavor, so just flavor entanglement, which means that we're going to have to make choices about kinematics and spin that we're just going to have to ignore. So we're going to make flavor entanglement, but then we measure kinematics and spin, so momentum and spin. And again, if ever someone comes up with a fundamental theory that actually describes all of this, hopefully it would be one for which I don't need to treat flavor and spin and momentum on a different footing. So I've already mentioned this, but scattering generically involves forward singularities. And forward singularities, especially when you have photon exchange, completely overwhelms anything that you're trying to do. And so we have to make a choice that kind of, the choice to avoid these. And again, you can argue about a particular choice to avoid. And then the issue that came up early on is like, what does the secant matrix even mean if you're in a limit where masses aren't that important? That we have to look at special states. So special states of definite flavor, special initial states of definite flavor. And so that also is kind of breaking the rotational symmetry among the three generations. So I'm going to go through each of these components in turn. Okay, I already have them. Okay, so the first thing is we're going to prepare our states. So we're going to start with states of definite flavor quantum numbers. So we have up, charm, top. Each one of those tensor product with down, strange, bottom. And so we have 9 initial states to consider. And just to emphasize, this is not the most generic, unentangled state that you can build. Of course, you could take linear combination of this, tensor product with linear combination of that. That would still be unentangled. But we're going to choose this particular basis, and then we're going to ask from this basis, which is unentangled, how much entanglement do you generate? And then the other choice that we're making is that we're going to consider all those 9 initial states, and then we're going to average over results. And you might say, well, why average? Why not take the maximum of all of them or the minimum of all of them? Okay, so those are choices that you have to make. But this structure, this avoids ambiguity of which generation of generation mixing, even in the massless limit. So they're choosing that frame. They're basically choosing kind of like an inertial frame for measuring your system. Okay, so that's the choice that we're making for preparing. Then there's the choice of what scattering processes we want to consider, because after all, even with those initial states, as mentioned already, if you have Higgs exchange, you have helicity flips and things like that. So I mentioned this already, but we're going to do elastic scattering. Elastic in the flavor sense, that is, flavors are always going to stay within this world. So elastic in flavor space. And so that leaves, if I'm doing UD, that's UD going to UD, or UD bar going to UD bar. But crucially, this means I'm not doing UU bar to DD bar. So even though crossing symmetry would say that these 3 would go together, I'm only focusing on this, plus the complex conjugate, which gives you the same answer. And that's because I want to make sure that I have a well-defined Hilbert space that I never go out of. So I want to start in a UD Hilbert space, and I want to end up in a UD Hilbert space to talk about generation of entanglement. If I had a UU bar Hilbert space, of course I could say how much entanglement is there in this state, but it's going from one Hilbert space to another. And we analyzed this channel, and it has interesting features, but it made things more confusing, so we're and I should say we're going to pick an interesting center of mass collision and everything. Pick an interesting, I guess, Rudess. And I'll show you the answers for all values of that. I'll just try to sketch it for you. Okay. So here is the part that is probably easiest to attack philosophically, which I've kind of already mentioned, but I'm going to be doing a measurement. And the reason why we're doing a measurement is related to this question about, well, what happens if you end up having 2 to 3 or 2 to 4 processes, that we want to kind of suppress that. So we're going to make a measurement, ignoring infrared singularities, make a measurement that forces me to always go from a 2-body initial state to a 2-body final state. Again, you can ask whether that's a reasonable thing to do. Certainly in a theory with that's IR regulated, that's perfectly fine. So measurement that forces 2 to 2 kinematics, and forces that we have only left-handed states, left-handed final states. And then, as I mentioned already, we want to avoid these forward singularities. So to avoid them, we're going to look at just one scattering angle. Again, you can ask, why not do an average over multiple scattering angles? You can look at that. But you need to avoid the forward scattering singularity. So if I have up and down coming in, and I have up and down coming out, I have to decide what angle I want to use for that scattering. And from the way I've drawn it, you can tell that I want to do it at 90 degrees, equals 90 degrees. So it's right angle scattering in the center of mass frame. And you get similar results as I already mentioned as you kind of move this around, but again, we're doing just a single value. And because of these measurement processes, this is a non-unitary measure, or non-unitary process. So this is a non-unitary manipulation, non-unitary process. But we're going to normalize states so that it's going to become quasi-unitary. That is, for each of these states that come in, for each one of those 9 combinations, we're going to renormalize, or sorry, not renormalize, we're going to normalize our states such that probability is conserved for each of those various channels after doing this measurement. So normally, you take up and down, you scatter, it's going to go off as an angle that's weird. Ignore that state. Angle weird, ignore that state. When the angle is right angle, you keep that one and then adjust the normalization of the state so that you have the appearance of unitarity, even though ultimately it's not
non-unitarity again because of the forward.
What?
Non-unitarity because of the forward.
Non-unitarity for multiple reasons. If you think about unitarity of the S matrix, right? Unitarity of the S matrix forces you to consider all possible directions things are going to go. Once you make a measurement, you're basically throwing out information, so that makes it non-unitary. And the reason why we're motivated to do something non-unitary is multifold. One is because we want to isolate the flavor component and not have the entanglement of the kinematics. And the other one is that if we let everything go, then the forward scattering singularity would completely blow up any prediction that we might have. So let me kind of draw more pictures of what's going on here. So you start off with a full Fock space. And if I had the full S matrix would take me from one Fock space to another Fock space. And this is the thing that satisfies the optical theorem. And ultimately, I would hope that whatever we're doing has a version where it's constraining just on the S matrix. But that's not what we're doing. We're isolating ourselves in this particular way. And so we have a projection of the initial state. We're not looking at all states. We're only looking at states that live in this flavored Hilbert space defined by this stuff. And then when you do scattering, generically, you would end up in a generic Fock space element. But no, we're also going to do a projection to the out state such that it satisfies these properties, such that at the end of the day, we have a quasi-unitary scattering matrix. This is now a 9x9 matrix in flavor space. And this thing is quasi-unitary, meaning that the diagonal elements, so normally a unitary matrix would say that it times its dagger is the identity, but here the diagonal elements of that thing is that identity. That means that if I choose any one of these particular states, I will get something where probability is conserved, but a generic admixture would not do that. Okay. Having done that, then we just borrow from the existing literature of people thinking about entanglement. So now we've pushed myself into this 9-dimensional Hilbert space, and there's various measures of quantum entanglement power. Or sorry, I think what I have in my notes is quantifying, various ways to quantify entanglement power. So our Hilbert space can be written as a tensor product of the up-type Hilbert space and the down-type Hilbert space. This is 3-dimensional, this is 3-dimensional, the whole thing is 9-dimensional. A generic state that I might get after the scattering would look like, so I start with something of definite up-typeness and down-typeness, but then after the scattering, this thing gets scrambled, so I end up generically having some of I of j goes 1 to 3, each of the 3 generations can participate. And then you take this object to measure entanglement, you want to look at the bipartite entanglement kind of across this barrier. So you take this and you build a reduced density matrix, for example, in just the up space. Or you could do the same thing, would give you the same answer if you did it just in the down space. And this reduced density matrix, because I've done things normalized, for the particular states that I analyze, this density matrix has the expected property that its trace is 1. But because I've generated some interesting entanglement structure, this reduced density matrix does not correspond to a pure state, corresponds to some mixed state. and therefore the trace of the density matrix squared is typically not 1. And in fact, that tells me that entanglement has been generated across this, this partition. And the particular one that we use that's popular in the literature is called the linear entropy. It's the linearized limit of von Neumann entropy, and we check that von Neumann entropy gives us the same answer. It's just that this is slightly easier to work with. So if I ask about the linear entropy of this state alpha, which is equal to some measure of how much this reduced density matrix squared differs from 1, this is some quantity that you can study. The value of this can be written in terms of some interesting eigenvalue structure. So I can take a matrix that I'll write down in a moment and look at this particular combination of eigenvalues. And then these eigenvalues are the eigenvalues of the matrix alpha dagger alpha, and these eigenvalues satisfy that they sum to 1, and that's just a consequence of normalization. And this quantity is a convenient one because you compute this alpha, that's what you get from the S matrix. You calculate alpha dagger alpha as a matrix, compute its eigenvalues, boom, you get some expression. And this object is something that goes between 0 and 1 for no entanglement versus maximum entanglement. And then, as I said, you take this object, average over your 9 options for the flavor initial state, choose some value of root S, which I'll show you a bunch of values in a second, fix the scattering angle at 90 degrees, fix that you're going to project down to left-handed states. And then something that I didn't say is that, and this is another thing you might worry about, is that what are you going to do with the channels? And then you're going to either sum or minimum or average of the channels. I'm going to minimize actually over by 2 channels. But from our paper, you could reconstruct what happens if you took the maximum. So many choices that we had to make. And in fact, we tried many different options just to see if it would actually work. And in this particular combination is the one that gives you the thing that looks like our universe. But
so if you made other choices, then
you get different results.
So
there's like absolutely a look-elsewhere effect. To defend myself a little bit, most other choices take the CKM angle and either put it, as I predicted originally, to be 0, or the Kibbe Weingarten to be 0 or 45 degrees. This combination gives you a value that is non-zero but also non-extremal. We fixed that in place, and they did the PMNS calculation. So in that sense, there's not a look elsewhere for that. That one really is a prediction. But I could have made many other choices, and again, this is my argument.
I mean, the one that's, a little bit arbitrary to me, it seems, is the 90 degrees. If you pick 45.
Oh, you get roughly the same answer.
Oh.
So that one we checked, and so the reason why we picked this particular angle is that you have to decide how much you want to average over, and because the photon is the one that dominates, depending on the scale that you have, to cut off the photon singularity part, you have to look at a different range of angles because it's the balance between S and T.
So you say if you shrink the angle, the photon contribution increases and you're driving it more towards 0.
You're driving the original entanglement measure towards 0 and therefore looking at minimizing it over, sorry, I should have said, and then finally we're going to then take this quantity and then we're going to minimize over BCKM and BPMS. So this is just the definition of the quantity. Then separately, we're going to make a prediction by minimizing over it. But if your angle is too small, then the photon contribution dominates. And then when you try to do the minimization, you find that you're not actually all that sensitive to the angle. And also you don't get what looks like what you'd expect.
Well, you
from
said
nature.
before you get theta equals to 0, right?
It
gets driven to theta.
It gets driven
theta
to
Kibbe equal to
it's either driven to Kibbe, either goes to 0 or to 45, depending on precisely other choices that you make. But it gets driven to extremal values.
Can you explain your choice of the measure? Because it looks like a measure of whether the state is pure or mixed instead of entangled or separable.
So if you want to know, remember, it's not this state that I'm asking whether this is entangled. This is just this is a pure state. I do scattering of a pure state, I get a pure state. The thing that I'm measuring the entanglement is the bipartite entanglement, the entanglement between up and down. And the way that you quantify, or a way of quantifying that, bipartite entanglement is you say, if I were to compute the reduced density matrix, how much does that reduced density matrix itself correspond to a pure state? And if it's not a pure state, then you would say that you have bipartite entanglement across this. Does that make sense?
Yeah.
Okay. So,
yeah, just to make sure, you are doing pure left-handed, left chiral state to left.
Right, and then left-handed, are we doing? Yeah, are we doing helicity versus chirality? And we're doing helicity.
Oh, not chirality.
Not chirality.
The interaction is chiral.
Which is why this question about the Higgs is making me spinning it back on.
Because I saw we're studying CKM. It's left-hand chiral interaction. I would stay with my chiral states.
That's right.
That's the most justified basis to do my calculation.
And because we end up choosing things that are far from mass thresholds, it doesn't matter. But this Higgs exchange thing is making me worried, which is good. We could have chosen chiral as well.
Yeah.
Part of the reason why we chose
What root S are you taking?
Also all of them. Also the values. We're going to be taking root S. At the end of the day, it's going to be kind of around the electroweak scale. So think about like 100 GeV, maybe the top quark 150, 175, something like that. High, and so the top quark is the one for which this distinction makes a big difference.
And also, I'm a bit confused about normalizing the state. What are you normalizing? You just divide everybody by same cross sections. Then they are differ by the CKM elements.
So what I do is for each. So I have my 9 initial states: up, down, charm down, top down. Okay, all those 9 ones. I scatter them, and then I do a projection where I only keep ones that are at 90-degree scattering, only ones that are left helicity, all that stuff, and that gives me some elements of my 9-dimensional Hilbert space again, and then but it's not going to be normalized because I've thrown out a bunch of stuff, and then I just normalize that thing back up. So it's the same thing that we do normally with collapse of wave function. So it's wave function collapse after making a measurement, where I throw out things that didn't satisfy the properties that I wanted. Just that, it's just that. Yeah. Okay, so. I'm gonna kind of wrap things up by showing kind of 3 things. So one, I just want to give you some intuition about entanglement, kind of what they want to do. Show you the plots as a function of root S hat, and then give you an outlook. So the first one, and this is basically the same, independent of all these choices of measures. But the most important thing to get the results that we have is that there has to be competition. So just giving you some intuition about entanglement competition. Okay, so all of them. Let me just do one of the channels. You can do it for the other channel as well, but it's a little extra time. So, okay, so let's start off with UD through a Z or gamma. So this is a diagram that suppresses entanglement. Why? Because there's no flavor changing nuclear currents. And so this diagram by itself doesn't have really a prediction associated with it in terms of what angles it by itself wants, but it allows large mixing angles because essentially this diagram doesn't constrain how much entanglement is. It already has very little entanglement. So no matter what CKM is, this one doesn't care. And its value will be something that depends a lot on interference. This diagram here with W, this one creates entanglement. And as already mentioned, it creates entanglement even if its CKM matrix is diagonal through VCKM. But if it weren't for this diagram here, this thing by itself wants small mixing angle. If this were the only diagram in the process. So this is the diagram that if you were following this earlier literature, if you had diagrams like this, because this thing creates entanglement and you want to suppress it, then you want the mixing angles to be small. That's the one that gives you symmetry. So this is the one, it's kind of a little bit backwards from maybe your intuition. This one creates entanglement, therefore if you're going to minimize it, this one wants things to be symmetric. And this thing doesn't constrain anything at all, so this is the thing that wants to be anarchic. And now it's the competition between these terms that depends specifically on the charges, whether I'm doing up, down, or if I'm doing neutrino with charge lepton, that gives rise to these different structures. Because it's not only competition, it's competition whose strength depends on the particular choice of charges. So another thing to say is that entanglement power is not crossing symmetric. One way of seeing that is in the channel that I'm not saying as much about, which is UD bar, which we've decided to include in our analysis. This one by itself creates entanglement even without CKM or VCKM, or without VCKM not equal to the identity. But this is more similar to what you would get from a bell pair, where you have some object and then you get kind of equal admixtures of the three things, like pi naught going to gamma gamma with that level of correlation. And so this one, you get interference with C gamma matters like a lot. And some of the funny features that you'll see if you look at our paper in detail have to do with the particular way that we're combining these things together. Okay, so now let me show you the results as a function of root S hat.
Just to confirm, okay, this S-channel diagram from W exchange, I can imagine even CKM is diagonal, it creates entanglement, right? But the left one does not.
Yeah, this one creates it through.
Yeah, only CKM.
Yeah, that's right. That's right. So this is again saying that entanglement is not a crossing symmetric phenomenon.
Sure.
And therefore, this is another way of saying that this study goes beyond the standard quantum field theory. With quantum field theory, we have the S matrix, and the S matrix has crossing symmetry and other properties. Here we're breaking that. So this goes beyond again the standard paradigm. Yeah.
But in the first set, the UD bar UD scattering,
yeah,
the Z gamma exchange allows large mixing, but they don't prefer large mixing, right? So any mixing
any mixing is okay,
right? So any mixing is okay, but then there's another diagram prefers it's an interference between them.
Then the final answer is interference. And
if it's not interference, I would symmetric.
That's right, and that is why we're writing this paper, is because there's this fascinating competition. So let me just show you what the answer is. So results. So as I said, for the CKM, it's only theta 1, 2 that matters. And we're going to show this as a function of root S hat. And if you're at very, very low energies, I forget what I apologize, I forgot to indicate it. If you're very low energies, and this is kind of related to Maxime's question before, like where precisely like the mass of the strange matter, it turns out that it wants to be 45 degrees, and then it drops, and then it rises like this. And this kind of dip here is roughly around mz, and the peak is roughly around m top. And the value of the peak is the 6 degrees that I mentioned, where we just pick that. And then in this region, once you go above m top, I'm not drawing it here, but you have kind of small values of theta 1,3 and theta 2,3 near the threshold that could appear. And we just chose, for the purposes of our study, just to report the number at that peak. But we could have reported the number a little bit off, then we would have gotten some small angles there. So let me just give you an intuition for how this works. So at low values of root S hat, so I'm down here, the photon dominates. So low values at root S hat, photon dominates. And you recall, a photon is the one that suppresses entanglement by itself. Therefore, you don't get a prediction, and then it's like the details, the vagaries of the interference that apparently drives it to be maximal. At high root S hat, you actually have a funny thing where UD to UD wants, if you like, mixing, but U D bar to U D bar does not. And so then exactly which channel you decide, whether you do this minimum over channels or maximum or some of the channels, that has an impact kind of over here for the precise values of the numbers. So, if we anchor things up here, as opposed to down here, actually, we would have larger variation having to do with the specific choice that we made.
But Jesse, the UD and UD bar scattering, they are normalized differently.
They're normalized differently.
And what's your choice to say
We take the minimum over them, and then the normalization is such that we normalize the states. We normalize the states so that that after scattering, the states are normalized to 1 always. So you're right. The cross section for those two processes is different,
right?
And we ignore that difference in cross section. You could have weighted by the cross section, but then you get confused about what do you mean by weighting by the cross section, because cross section, we're doing this funny measurement. So what do I mean by a cross section?
Yeah, so you normalize them separately.
I normalize them separately, do the analysis separately, and then in the paper we show the answers.
Then you minimize entanglement by treating them the post-normalized entanglement on equal footing.
That's right.
And here on every point of this curve, the entanglement is minimized, right?
At each point along this curve, I'm choosing to minimize entanglement, yeah.
So, just out of curiosity.
Yeah, you can average over the whole thing.
No, I don't mean, well,
Yeah.
I suppose you could do that too, but it passes through 13 degrees. Right?
Oh, absolutely.
And what
it passes
happens
through 13 degrees right here, and then, yes. Wouldn't that's another thing you do. I haven't looked at it when it passes through here. I'll do the PMNS in a second. Actually, that'd be amazing. Where it passes through 13 there, it turns out to be what.
Yeah, but you also then have, this is just theta 1, 2, so what does it give for?
Oh, so the other ones are 0, and then it does some funny business.
Oh, okay.
Yeah, so unfortunately, you don't get the other ones. Yeah, that would be too amazing.
Jesse, this slope, right? I understand there are thresholds, right, of your entanglement entropy. So I would expect jumps, right? There's coupling running. But this slope seems to be very big. What is driving that slope?
So
below the left one, yes.
The left one?
Yeah.
So that slope is being driven by the photon diagram becoming more and more important. So here, if I had just Z exchange and W exchange, then these two diagrams are roughly the same size across the whole range. That's what gives me the 13 degree prediction. So
it's really E over mz squared, E squared over mz squared.
E squared. Yeah, exactly. It is the relative strength of photon versus Z, and photon dominates, and it just wants a different structure. If you could explain to me why I can just ignore the photon contribution. After all, we're breaking quantum field theory, so might as well just drop things randomly. Then we can give you 13 degrees. Okay, so then for PMNS, the structure is a little bit different. So for PMNS, now actually all 3 angles matter. So this is a little bit bigger. For PMNS. So again, maximum at 45 degrees. And we have the tau threshold here. By the way, these plots, root S is being drawn on a log scale. So we have the tau threshold, and then we have Z here. And below the tau threshold, you can't make taus. And it happens to be that what that wants is 2 large angles and one that doesn't matter, or 0, because I can't access that 3rd generation. Then this one drops, this one rises, in fact crosses over, and this one falls like this. And I'm drawing, I need to get this thing to look, we have 2 similar angles and one that's lower. So using this to decide which one corresponds to tau. This is what I have the theta 1, 2 and theta 2, 3 up here, and they're roughly around the same at 29 degrees. And then this one down here, which is theta 1, 3, this again is the one that's around 16 degrees. So indeed, where this thing crosses 13 goes a little bit closer, if I were to go like somewhere like that, like it goes a little bit closer where now of course the lines are crossing in some way, but anyway, it would be worth me checking that. Maybe it doesn't go closer, maybe I'm, but anyway. But it's dependent on root status, and then you say, well, why is it much smoother here? Again, this thing is coming from the photon contribution, but mass thresholds don't matter. Here, the tau threshold really matters, so this is just mass threshold, but the photon doesn't. But in both cases, you see that affects the structure of the final answer. Okay.
Don't I expect something strange to happen around W and Z poles?
No.
No. There are signs flipping.
They're in the T or the U channels, so they don't, you're not making them. And so all it does is change the value of the propagator a little bit. Remember, they can never go on shell in the T or the U channel, so there's no enhancement. Okay. So with that, let me kind of sum up what I told you. So, as I mentioned at the beginning, I've never really worked that much on flavor physics, and in part I haven't worked that much on flavor physics because trying to post-dict the values of the CKM and PM&S angles, or the masses of particles for that matter, all the models I'm aware of have conservation of free parameters, and that while I might be able to explain hierarchies through some Nielsen mechanism, getting the precise values seemed like I just had to twiddle knobs until I got what you wanted. Here, we are achieving all these predictions all at once because we're minimizing some quantity. You might say, why minimizing entanglement? It's because we're motivated by other people who have studied entanglement in the past. But minimizing of anything can make multiple predictions at the same time. Now, if I was talking about minimization of energy, you would get super excited, right? Because when we're talking about minimizing the energy of a system, then this is more like what we know about for the strong CP problem. For the strong CP problem, we take theta, we realize that the energy of the vacuum depends on theta, and so you minimize the value of theta, you get theta bar to be 0, and then you have a prediction of another particle that actually corresponds to you'll be able to relax and having the axion. So if I'm talking about minimizing the energetics, then you would be happy, and then you'd be excited about seeing some kind of flavon fields. In fact, instead of minimization, people who work on like flavon type dynamics oftentimes are spontaneous symmetry breaking, which is not so dissimilar from this story. Okay, but because we're talking about entanglement, minimizing entanglement, it's not clear how that could possibly be a dynamical phenomenon. Who ordered that as something that seems to be correlated, at least with the rough structures of what we see, and kind of how could that possibly be a fundamental principle of nature? And what I'm hoping is that you'll just find, as you explore this more, that there is some more meta principle that would explain why we're seeing these coincidences. So again, it's not obvious how to make this a dynamical story. It's also not obvious how to turn this into making additional predictions, with one exception, that the prediction that we got if we take this neutrino story seriously is that we'll have a CKM angle of pi. So if you're a Dune enthusiast, minimizing CP violation might not be what you would prefer, but okay. And this issue about how you even define things at high orders, it's kind of a really pressing one, not just for this story, but anyone who's studying scattering amplitudes. When you're studying scattering amplitudes, what's the infrared dynamics of your theory? And especially if you're using concepts from quantum information theory like entanglement, which were built for finite systems, going to this Fock space picture, it's really not obvious what to do.
But doesn't that back up your claim that if you get rid of the photon, you get it spot on, right? Because that's a question of
the infrared dynamics. It's infrared, but that's in the T channel. So it's not gapped out, and I haven't actually thought about if I did a cavity QED calculation whether I can gap this thing out. But anyway.
But the left-hand sector, you don't have the photon.
Left-hand sector, I don't have this beautiful structure.
Yeah.
And it's actually quite it's more robust. However, still at high orders, I go to one loop, then the photon comes back and back. And now you have a charged lepton with a little bit of photon. generically, entanglement is destroyed when you have radiation. Coherence is destroyed by radiation. So if you're taking entanglement as your measure, and now you have all these things that can destroy it, then that also becomes problematic.
And what's the asymptotic prediction of your
I think
static?
I think if I remember right, I think we can look at the paper. I think both of these things go to one value, and this one still stays low. I think that's what it does.
And for the
And this one, I think this one gets. It depends on which channel you want. So what did I say?
your average over
I
two
said-
channels
okay,
are ideal.
so this one, this one does not want mixing. So this channel is the one that dominates the entanglement. So this one doesn't want mixing. So I think asymptotic, I think it's still goes to zero. Which by the angles go to zero, goes to diagonal. Which again, you could say that's of course not what nature has a non-zero equal. But I think the thing that's just remarkable to me is that leptons and quarks. This is the reason why leptons and quarks behave differently. That is, I've never heard of anyone talk about the charges as being the thing that drives their differences. It's normally, well, of course, they're representation of different, but anyway. But you know, perhaps we have somehow accidentally stumbled across a harbinger of a new principle of nature, or maybe Hinchley's rule is true, and we'll have to see. So, thanks very much for your time.
Is there a maximum to the entanglement?
By definition, the maximum entanglement is defined to be 1. And so maximum entanglement is exactly what you expect. It's like equal contributions from all 9 channels. We give you maximum entanglement. And then you could ask, do we ever achieve that? Like, is there any value of the kinematics and the scattering that achieves that? And that I don't remember. The values, my recollections of the values are like 0.2. Is the kind of typical minimum values, if I remember correctly. So you don't really actually get that close to the maximum value of entanglement with the electrode processes.
So in literature, when people maximize entanglement, do they use different definitions?
So the people who got the theta Weinberg from maximizing entanglement, what do I say? Here's what they do. They take 2 different scattering processes, and they say, I want to maximize entanglement, subject to the constraint that entanglement is maximized at the same value of a scattering angle in 2 separate independent processes. So you have, in our case, we fix the angle at 90 degrees. What they're saying is, choose the angle of scattering such that 2 completely separate processes have the same value of entanglement and then maximize there, which is a weird correlation there where I don't know how to justify it. Of course, I don't know if it's any more justified than what we're doing here. I mean, what they found is that there's I think the fair way of talking about both our work and everyone else's work is that there is clearly some interesting behavior of this quantity of entanglement on fundamental physics parameters. That's certainly true. Whether you can then turn that around to making a prediction of fundamental physics parameters, that's the part where all of us are making some ad hoc choice, and we're making, and obviously, we are very blunt about this, we are making the choice that corresponds to what we see in nature. And we wouldn't have written the paper had we gotten fully diagonal. So there's absolutely a selection effect there. But you know, roughly speaking, everyone's measure of entanglement secretly has some element of, you prepare particular states, you're doing some type of specific type of measurement, and so on. The big difference between what we're doing and the folks who are minimizing entanglement and finding these enhanced symmetries, for example, in baryon scattering, is that there you can make the entanglement 0. And when the entanglement is 0, basically, if there's no entanglement, then every measure of entanglement, every choice you make will always give you 0. So that's where they benefit, is that they are more predictive because they get the actual measure of entanglement, whereas for us it's like 0.1, 0.2, something like that. For them it's dead 0, and therefore any linear combination of the components that go in it will still give you 0. But again, they find enhanced symmetries, which is not what the flavor sector wants to do. So we are the ones who had to really think a lot about what choice we wanted to present. And we have a subsection that really is just very honest. We have a look elsewhere effect. And you should be skeptical because of that.
Why don't you go back to the interaction basis then? Now the mass matrices are 3x3 complex.
Mm-hmm.
And now you exchange the Higgs. There's also flavor changing there as well.
In the interaction basis.
Exactly. And then you can also look for minimizing quantum the entanglement. And but there you don't just get the CKM, you would also get the UCALs.
Absolutely.
And that would actually put everything together, right?
That would be the hope.
Because now you have 36 parameters, right?
Yeah.
Because you've got the up and down neutrino and electron.
Yeah.
36 parameters, see if there's any correlation.
Yeah.
Then you would diagonalize
Yeah.
that system, and then you would get the whole picture.
And so you can ask why we didn't do that. Part of it is out of laziness, but also once you start thinking about Higgs interactions, now you can no longer talk about flavor independent from helicity and spin. So then your Fock space is one that has both flavor and spin information. So instead of being 9 by 9, now you're talking about 3 times 2.
It's
6.
It's
36
It's
by 36.
36.
So it's a 36-dimensional Hilbert space.
Yeah.
And there's nothing that stops us from doing that. Absolutely, we could do that. It would be an interesting thing to do. We had to
have a comment.
Actual thing to try to figure. Yeah.
I have a comment in this respect. So if you look at the old semi or entirely numerological literature, some of it can be phrased as what is the maximum number of zeros I can put in the Yukawa matrices so that I get a reasonable phenomenology, right? And it turns out that with Yukawa matrices with lots of zeros actually describe the relation between numerological relations between masses and quark mixing angles quite well, actually, right? And all that story, as per what Tony said, you can probably rephrase in terms of the scattering amplitudes and the weak bases, and killing a maximum number of diagrams, if you like, right? And I hasten to say that it all goes back to Weinberg, who had a paper that the sine theta Kaviva is the square root of MD over MS or something like that in the early 70s. So you should have a look at that.
Yeah. So this is an excellent point, and obviously we're not the only people who've done numerological studies. I think the example of what we were just mentioning of kind of this prediction for Kabibo, the modern or the extended version of that are Froget-Nielsen models, which also you're trying to get kind of the masses, and those, if you're willing to change those charges, right, you can get a prediction that's reasonable. And so maybe something that we should think about is whether actually the values that look like those kind of effective charges, what they really look like is they look like the values you would get that would minimize a particular.
Froget-Nielsen wants a little bit more, right? It wants to explain everything in terms of the charge assignments, horizontal groups, one order parameter lambda, right? What I was referring to is just people trying to take one Yukawa matrix diagonal, so lots of zeros, right? And the other one is arbitrary, but with a maximum number of zeros you can tolerate based on masses. And I forgot, it's called a Fritsch ansatz or something like that. And at the end of the day, it actually gives reasonable ansatzes for mixing angles once you start putting information about the diagonal masses, right? And it's not playing with the hierarchy as such, but maximizing the number of zeros. And that's why it kind of smells similar a little bit, have the flavor of what you're doing.
Excellent suggestion. We'll definitely have to look into that.
Okay.
Anything else? Yeah.
Oh, I have a question.
Yeah.
Assume this picture is correct.
Yeah.
That basically means if we can change the generated entropy, we can more or less change these all angles, these coupling constants, right? So if I have a way to really change the let's say we couple the initial state with a new qubit or something, and we just twiddle it, and we can change the generated entropy. Does that mean we can actually change the effective theta angle or something?
Oh, okay, so good. So what you are saying, if I understand correctly, is you're saying, let's say we take really seriously this idea that the parameters of the standard model are determined from this principle. And now you want to play with the principle, that is, you want to say, like, or you're talking about like really thinking about this like dynamically in the early universe, like coupling to some hidden sector and like that kind of correlation. Right, so basically another way of saying this is, if you take this thing seriously, then there's very interesting model building possibilities that one could explore. And Socrates would love this type of thing. So for example, he wrote a paper recently with my student where the prior was that there's some mechanism in the universe that favors metastability. That we say, we don't want a stable vacuum, we want a metastable vacuum. Prior on wanting a metastable vacuum, if you do that, then there's interesting BSM implications. But of course you have to say, well, where was this prior coming from? But this would say, prior to this, saying that the entanglement is important, could you, like, for example, figure out a way of explaining, or use that as an engine to try to make predictions in a BSM scenario? I think that's kind of where you're getting at. That's an interesting thing to consider.
Or we can do experiments just to prove it, if it's true.
Right. Do experiments to prove whether it's true. Well, we can't change the fundamental parameter of our universe, but I think you could imagine saying, I'm in a physical system. I build a physical system with some number of free parameters. But what's confusing is those aren't. There's no way. I don't know of a dynamical way for them to relax. Is maybe the problem. But that's the issue. Is that here I say I'm looking at this correlation, but what's the mechanism by which you would actually, for example, cosmologically set the values such that it would want to do this entanglement minimization? In the case of the work that was done on octet baryon scattering, there the words you would say would be different. There you'd say you start off with some fundamental theory of QCD, and then in the process of the confinement strong dynamics, then you find that entanglement wants to be minimized, and then you might imagine that strong dynamics has a preference for something. That would be but the dynamics is the strong dynamics, and that might have a preference for minimizing entanglement. So in that story, it's a little bit more intellectually coherent. Because you have a dynamical mechanism that could make a choice. And because it's non-perturbative, you can say whatever you want about what it might be. In our case, everything is perturbative, and we don't see a mechanism to move these parameters around. But maybe that's the way to do it. Maybe there's some kind of, you couple this to some scalar field in some way, and that somehow that scalar field, I don't know, it's maybe not energy minimization, but free energy minimization. So you get some kind of entropic something or other going on. I mean, yeah. This is a widget to explore more, whether it's valuable.
Can you do this for eta eta prime mixing?
Can you do it for eta eta prime mixing? So what's the parameter? In that case, this is like the contributions for like some instanton compared to.
Well, I don't know. I mean, you have octet and singlet mixing, so you're.
Yeah. So I don't know that I don't know whether you could use it for eta eta prime. That's interesting. That is, imagine that you took the chiral Lagrangian, augmented it with an eta prime, and then saying in that low energy effective theory, is there a preference for what we see? That's interesting. I don't know. But then again, in the context of strong dynamics, where it's spitting out those states, you can say, oh yes, the dynamics happens to be the one that likes.
I mean, there's lots of them, right? Because in the Meson sector, there are lots of mixing angles.
That's right. It's also true. Yeah.
Great. I think we had a lot of very, very exciting discussions and many more things to explore.
Okay.
So thank you, Jesse, again. So I'm still, what you choose heavy city states?